Okay, we're going to look at trig derivatives. All right, so the derivatives of sine, cosine, and tangent functions and their reciprocal functions. Okay, so secant, cosecant, and cotan. So we're going to first look at sine. So sine of x. We're going to look at this from a very initial perspective. So we're going to look at the average rate of change. Okay, so very basic approach to this is f of x plus h minus f of x all over h, where h is the difference between the 2 points. So we've looked at this early on in the course. And the first way we did this was by looking at these tables that we made. Okay, so we're going to look at the average, looking for the instantaneous rate of change, which means the derivative of f of x at 0. So this is going to be by taking a look at the table that we're going to make for the average rate of change. Okay, so we're going to set this table up for sine of x as this. Now this is for when x is in degrees. So let's take a look at this in degrees. So in degrees, I'm going to make this go from negative 10, negative 1, negative 0.1, 0.11, and 10. So we're going to take a look at this as it sort of collapses to the center. So the instantaneous rate of change would happen at x equal to 0. This is our way to get an approximation. So the average rate of change between x equals 0 and x equals negative 10, basically, is going to be, if you plug that into your calculator and work this out, you're going to get negative 0.01736 approximately. Okay, if you keep working these all out, you're going to get these numbers. Okay, so these are approaching a certain value, which we can't really tell what it is. So 0.17453 on both sides here, but there is a pattern. So from this pattern, we can basically now make a prediction that the instantaneous rate of change is approximately 0.01745. Now, if you pause for a second, you can put on your calculator pi divided by 180 and see what you get. Okay, so you'll notice that pi over 180 is actually this value. So it's interesting that the instantaneous rate of change, or the derivative of sine of x at x equal to 0, is pi over 180. That's when we work in degrees. If you work in radians, well, we're going to use a different scale here. Instead of going negative 10, we're going to go negative 1. Because negative 10 radians is really far back with respect to one full cycle. Negative 10 degrees is a very small part of the sine curve. Okay, especially when one cycle takes 360 degrees. But in radians, one full cycle only takes 2 pi, which is 6.28 units. Okay? So we're only going to go back 1 unit here, which is actually more than 10 degrees. Okay, if you think of it in terms of proportion of a cycle. So negative 1, negative 0.1, negative 0.01. Plug those into that formula up here. Okay, but your calculator is in degree mode, and the function is sine x. And you're going to get these numbers. Okay. Now these numbers seem to be approaching a much nicer number than 0.01745. So they seem to be approaching the value 1, and in fact that's what it is. Okay, so the IRC, the instantaneous rate of change at x equal to 0 of sine of x is 1. Okay, so the slope of the tangent at 0 is 1. Now when you look at the sine function, okay, so this is the sine function, notice that the slopes of the tangents on opposite sides here are the same. Now that makes sense based on the shape of it. If that's a, then negative a would have the same sort of shape opposite way, and the tangents would be the same. Okay, or the slope of the tangents would be the same. If we look at the slope at x equal to 0, it's 1. So the equation of the tangent here would be y equals x. And that would make sense for the function when you do it in radians, for sine of x when you do it in radians. However, if it's in degrees, it is a really small slope. Okay? Now thinking of this as there's 1 on the y-axis. There's about 6.28 on the x. That being a slope of 1 makes some sense. But to go 360 units, so if that's 1, if it's a 1-to-1 scale, okay, that would go way off the page and way off the screen for one cycle. So by the time you went from 0 here to the edge of the page, you would be barely off the x-axis. So the slope would be really low if it was in degrees. Okay. Now, there's 2 limits that you should try to work out. I'll show you what they are. And then, okay, so try to work out those 2 limits, basically. So the limit is h goes to 0 for each one of those. And once you've got it, then stop pausing and come back in. Okay, so the limit for both of those is given here. So the limit of this one is 1. The limit of this one is 0. So if you plug in values really close to 0 and look for a pattern, this one tends to 0, this one tends to 1. In fact, this one's kind of interesting to look at because sine of h around h equal to 0 looks like y equals x. Based on what we looked at here, the tangent is y equals x. So right around 0, this function might as well be y equals x. So around 0, sine of h is basically h. h over h is 1. Okay, so even though this is a 0 over 0 limit, it looks kind of like h over h, which is 1. And 0 over 0 limits have a hole in them. So basically they should have they most likely will have a limit. This is 0 over 0 as well, so you've got to plug in numbers. Now we're going to use these to try and find the derivative of sine of x in using the limit definition. Okay, so sine of x is the function, then f prime is the limit as h goes to 0 of sine of x plus h minus sine of x all over h. Now we have to use this formula here, sine of a plus b. It's compound angle formula to simplify this sine of x plus h. Okay, so here's the formula for the compound angle of a plus b. So we're going to put an x and h into those. And we get this nice expression here. Reorganize it a little bit. Bring the sine of x over with this sine of x so we can factor it out. And we've got this. Okay, so now we've got a sine of x as a common factor here. Factor that out. Okay, now we have cos of h minus 1 and a sine of h over h, which looks kind of like these limits that we have here. We just have to keep organizing it a little bit more. Okay, so you can break that into 2 fractions. Okay, because h is a common denominator. And then you can distribute the limit in. So you can distribute the limit into almost everything. Okay, so we're going to distribute the limit in. And once we distribute this in, again, we notice that sine of x is not dependent on h, so we can bring it on the outside. Same with cos of x, not dependent on h, we can bring it to the outside. We're going to have the limit of these 2 pieces. Okay, now those are our special limits that we just evaluated earlier. That one equals 0, that one equals 1. So the derivative of sine of x ends up conveniently being cos of x. Okay. Now, for f of x equal to cos of x, the derivative conveniently ends up being negative sine x. So not sine x, but negative sine x. And you should be able to prove this using the same method that we did the last one. Okay, in fact, I'm just going to flash the proof here for it. So this is for cos of x. Okay. And the derivative is negative sine. It also uses a compound angle formula for cos of x plus h, which is this one here. Okay. So if we've got the derivative for sine x is cos x and the derivative of cos x is negative sine x, then now we should be able to figure out the derivative of tan x without the limit definition, because tan x is sine x over cos x. Okay? So basically all we have to do now is the quotient rule. So the derivative of the top times the bottom minus the top times the derivative of the bottom divided by the bottom squared. So derivative of the top is cos x times the bottom minus the top times the derivative of cos x, which is negative sine x, divided by the bottom squared. Okay. And simplify that, we get cos squared plus sine squared on top. We know what that is. That's an identity. Okay, over cos squared. So that equals 1 over cos squared, which is 1 over cos is the same as secant, so it equals secant squared. Okay. And the next derivatives we're going to look at are the derivatives of the reciprocal functions. Okay. So secant x, again using the quotient rule, you get derivative of the top times the bottom minus bottom times the derivative of the top over the bottom squared. That simplifies to sine x over cosine squared. Break up the bottom, and sine over cos is tan, and 1 over cos is secant, so you can just write that as tan x times secant x. Okay. Similar pattern for cosecant x. Okay, you get negative cotan x, cosecant x. And then cotan is cos over sine, so use the quotient rule there. And you get negative cosecant squared of x. Okay. So, a few examples to try here. So the derivative of sine squared of x, same as sine of x all squared. Using the chain rule, we take the 2 down in front, reduce it by 1, so that's 2 sine x, then times the derivative of the inside. The derivative of sine x is cos x. Okay. Now if it's the x squared, the x that is squared, well then we take the derivative of the outside, which is cos x squared, times the derivative of the inside, which is 2x. Okay, and we rearrange that to equal to 2x cos x squared, usually. Okay. Something like this, f of x equals cos of sine of x squared plus 2x. So this is a nested chain rule. Derivative of the outside is going to be negative sine. Okay, so that's the derivative of the outside with respect to the inside. Now we're going to take the derivative of sine of x squared plus 2x. Okay, so derivative of sine is cos x squared plus 2x times the derivative of the inside, which is 2x plus 2. Okay, a lot of organization here. Something like this one, cosecant squared of x cubed plus 7. Well, you can take this squared on the outside of the whole thing if it's easier to look at. And so the 2 comes down in front. Power is now 1. And then the derivative of the inside. So the derivative of cosecant is negative cotan cosecant. But you can't change the variable inside yet because that's still a chain rule. Then you multiply it by the derivative of the inside. So the derivative of x cubed plus 7 is 3x squared. Okay. And something like this one, if you want to take the derivative, looks like a product rule. Could be a product rule, but if you look at it closely, you could use an identity to simplify that. So simplify that to just sine of x, and then the derivative of this ends up being cos of x. So that's it for that lesson.